All right, we have a low, I mean, people maybe are brain out or brain in. I don't think so. Anyway, I'm very excited to hear Michael Chapman's second talk, and hopefully, I don't know.
Let's see what happens.
Let's see what happens.
Okay, so this is a second talk on the lineal Meshulam complexes. And let me quickly recall what is the model, and just to remind you all that we're talking today only about two-dimensional simplicial complexes. So they have vertices, edges, and triangles. So it's a graph where you paste some triangles over closed paths of the tree. Okay, that's the data that you get. And how do you sample such a thing according to the model? So a y sampled according to the linear Meshulam model with parameters n, where n is a natural number, and p is a number between 0 and 1, is the following. You take all possible vertices between 1 and n, then you take all possible edges, so the underlying graph is the complete graph, and then you can paste essentially every triangle you want, and you paste the triangle with probability p independently of all others. Okay, so each triangle is just with probability p in, with probability 1 minus p out. Okay, so this is the model. And last time we discussed connectivity of these complexes. So in which parameter range are they connected? And we said, okay, what does it even mean to be connected? And we said that in the zero-dimensional case, you can either think of it as there's a single connected component, or there are all cuts in the graph are non-empty, right? These were the two conditions. And one we said, okay, you can generalize it using cohomology, and one you can generalize it using the fundamental group. And I want to recall the fundamental group definition, because the cohomology I'm going to redefine completely and generalize. Okay, so today's talk is kind of a generalization of the cohomology of last time. But what was the fundamental group? So a Van Kampen diagram is just this tree of disks that you draw in the plane, and you give it a simplicial structure. So this is there is a graph here. So these edges may be paths of some length, and there are like vertices on the circumference of the disk. And each disk is also triangulated with all the triangles inside, okay? And this is a Van Kampen diagram of a simplicial complex if you have a simplicial map between them. And I defined last time what is a simplicial map. It just write down names on the vertices between 1 and n, or whatever the vertices of x are. And if whenever you see an edge here, it actually appears here, and whenever you see a triangle here, it actually appears here, this is a simplicial map, and this just, you call it a diagram of the simplicial complex X.
Also vertices on the inside of the triangulation?
Yeah, you also need to label all of them. Label all possible vertices that you see here, and this gives you a potential mapping on the level of vertices to here, and it is a simplicial map if it extends to edges and triangles appropriately. Great, and then we defined a few parameters of this diagram. So this diagram, not alone, but with this mapping to X, so with the labeling of the vertices and the edges and the triangles, we said that the circumference of the diagram, so it's not well defined, it's well defined only if you pick a starting point and orientation. So you choose some starting point on the outside of one of the disks or on one of these edges, and you start walking either clockwise or anti-clockwise, but you do this path that just goes around this thing, all around, until you come back. And this is some closed path in the simplicial complex X, and this closed path is called the circumference of D, and we denote it by gamma for now. Okay? And then you can associate two other parameters to the diagram. One is the length of the diagram, which is just the length of this path, just how many edges did you walk over along this path. And you can associate the area of the Van Kampen diagram, which is just how many triangles do you see here. Okay? And then we said, okay, let's flip the script. Let's start from a closed path here and ask ourselves, out of all the length of a path here is well defined without any Van Kampen diagram. But the area, you can define the area of a curve, of a closed path, to be just the minimal area over all possible Van Kampen diagrams with this circumference. Okay? This may be empty, and then we will say the area is infinity. Okay? So when the area is finite, there is actually a Van Kampen diagram for gamma. We call gamma contractible. Yes, Simonyi?
Maybe like an example, maybe you can say about like a torus or something.
So I'll do it in a moment, okay? That's actually a good remark. Okay, let's even do it now. I even have it in my notes, but I didn't write it down. So, like, this notion of contractibility is a combinatorial way of viewing the following purely topological idea. That, for example, there are closed paths which are actually contractible. What does it mean? It means that, for example, if you take this path on a torus, you can actually like continuously deform it until it becomes a point. Okay, so you do like, you make it, you shrink it and shrink it and shrink it until it becomes a point. And then you call this path contractible. But you can go over this path that goes around the hole, and you can check, or at least convince yourself, actually, mathematically, doing it is not as easy, but you can at least visualize that you cannot contract this thing, okay, to a point. Like, because it will go around and you will try to contract it, and no matter what you do, if you do it continuously without cutting the sides, you won't be able to contract it to a point. So it's not very hard to triangulate the torus. And then you can actually take paths in the underlying graph of the torus that are comparable to this type of thing, or comparable to this type of thing, and you can check that the area of these ones will be infinity and the area of these ones will be finite. Great. And actually, the torus is a good example also for the second definition that we had last time, which is hyperbolicity. So we said that a simplicial complex is hyperbolic. That's actually a property of its fundamental group, but I'm avoiding groups altogether today. All properties will be properties of the simplicial complex. So a simplicial complex is hyperbolic if there exists some real number, positive real number, that satisfies the following. If the area of a closed path is finite, so if the closed path is contractible, not only it's finite, it's bounded by, in a linear fashion, by the length of the path. So if it has a contraction, it has a small contraction. And the smallness is compared to the length of the original path. Great. And then we last time saw two things. So I won't recall what is the cohomology group. We will do it in a moment. But we saw two results last time. One due to Babson, Hoffman, and Kale from 2010. One by Linial and Meshulam from 2006. That gave us the following picture. And I'll try to keep this picture on the board throughout the talk. So this is not the exact thresholds, but up to the exponent and polylogarithmic terms, it is the correct places. So we saw that substantially above 1 over half n, 1 over square root n, all closed paths are contractible. And the way we did it, if you remember, we took two links and we looked at their intersection, and we said that further here, the intersection of links is connected, and somehow we use that to triangulate every closed path. Okay, so this was this parameter setup. Here on the left, this is due to Linial Meshulam. We said that there are isolated edges, right? And then the cohomology group does not vanish. And actually, whenever you have an isolated edge, you can see that any closed path that passes through this edge is non-contractible. Okay. So actually, this shows you that, okay, there are non-contractible paths. But actually, even here in the midpoint, in the middle range, we saw that on the one hand, the cohomology group vanishes. This is the Linial Meshulam result. But two properties of the complex we know, asymptotically almost surely, so with probability tending to 1, the path 1 to 3 is not contractible. So clearly with high probability, we said that the specific triangle will not appear there, right? We will not paste a triangle here, just because these numbers tend to 0 when n tends to infinity. But even more, like you just cannot triangulate with probability tending to 1, you cannot triangulate this path. You cannot find a Van Kampen diagram for it. But we said one of the properties that we needed, okay, that Babson, Hoffman, and Kane needed, was that actually with asymptotically almost surely, the simplicial complex that you get out of this process in this range is hyperbolic. So these are the two.
This was needed for like a more sophisticated union bound argument.
So we said that actually you cannot do it with the union bound, but I try to give you like a hint of how is it even helpful. And this is helpful in the sense that, okay, now you want to triangulate 1, 2, 3. You need to somehow say that it cannot be triangulated only up to 3 row, right? Like if you have this type of row, where is it? This type of row, clearly the length of this path is 3. So you don't need to check all possible triangulations. You need to check only short triangulations. And then they don't really use a union bound. They use some other method, but they like show that at least the short ones cannot be done. And because of hyperbolicity, the long ones also, like the high area ones, are not there because of hyperbolicity. So this is just non-contractable. So this was somehow an infrastructure, like how do you say, pigumim.
Infrastructure.
Yeah, so it was like the infrastructure.
Scaffolding.
Scaffolding, thank you. So this was the scaffolding for this, but actually today I'm going to use it just on its own. The fact that this simplicial complex in the mid-range, I'm calling this middle part the mid-range of the density of the triangles, okay? Yes.
Yeah, I have 2 questions. One is, so your torus example is not triangulation, it's not like 2-dimensional simplicial complex, right?
Mine is not, but you can do it, right? Like you want us
No, that's fine. I just want to double check that in that case, like in the continuous space, this hyperbolicity is saying like the area it contains is at most row of the length.
Yes.
Okay.
Yeah.
And
but okay, so the torus is not hyperbolic. You can check on your own, okay? That's not a hard thing to check, but that's exactly because like the plane is non-hyperbolic. So just
the torus is like the plane, and in Euclidean plane,
yeah,
the circumference is square root of the area.
Exactly. So so the whole point is that if you so I can even give you the path that you take. Just go around here n times. Okay, then go around here n times, then go in the other direction n times here, and in the other direction n times here. You get something that has a finite area, but it's finite area, so the length of this thing was 4n, and you can convince yourself that to actually fill this up, you need approximately n squared, something on the order of n squared.
That's super complicated. Why don't you need to do that?
Yeah, you can do that.
That's exactly like in the grid. How do you convince me that you're not hyperbolic? Give me very large squares or rectangles,
Yeah, sure.
and that was how, the way I described it. This is exactly a very large square in the plane.
Why do you need
Why do you need to go around? You can just go.
Because that's the way you make the length large. How do you make a length large if you don't do something a long time? You need large lengths. So me going around n times is the same as taking this.
No,
This is length n.
It's really not. Maybe you're thinking group theoretically, but really, like, if you have a triangulation of the torus that uses only 10 triangles, then it's meaningless. It's only meaningful when the number of triangles that you use is like n.
No,
or n
You're
squared.
wrong, because you can use the same.
No, you're completely wrong. The Van Kampen diagram of this thing is well defined. No, for finite many triangles on this thing, and exactly you need this type of thing of going n times to show that you use larger and larger squares.
I see.
So it's a fixed simplicial complex. It's a property of a single simplicial complex with finitely many triangles. That's very important to me. So it's not as if you can see it by just going like once. You need to somehow take long length contractible paths. And the way to do long length contractible paths is exactly taking the commutator of higher and higher powers of going around the hole in this way and in this way. So that's comparable in the plane to taking very large
So
squares.
you're saying that even if your simplicial complex has a constant size,
Still, hyperbolicity can be
true or false, even if
Yeah.
I allow myself rho to be
Yeah, there is no, what we just showed is that for the torus, if you take any finite triangulation of a torus, there is no possible row here. No row will satisfy this condition. Although it's a finite
So
object.
that's very different from like in expansion. If I have a graph on a constant number of vertices and it's connected, it's already an expander for sure.
Right.
Because I only consider things of size up to the size of the graph.
Right.
I never consider like.
It's not an infinite collection. So here there are infinite collection of closed paths. And this condition is a condition on infinitely many things. And actually in the cohomology thing that we will do today, so today we will going to talk about covering theory, which is closely related to all this pi1 and non-contractible paths and stuff like that. And the same type of phenomenon will appear. Although you have a finite object, it can somehow not be an expander in exactly this sense. Like it
But I've
can.
always wondered
Irit,
about
I think what would solve your issue is that you should take the universal cover of the complex.
Yeah.
And then you have it as something infinite, and then you can define everything there, and then I think you get the same.
Yes,
thing
like
that you're
this
using.
definition is equivalent to the universal cover of X, which is an infinite object in the case of the torus, being hyperbolic in the regular sense of a metric space, and then like you can take again, but you
I
need
just
to
want
take.
to say though.
Yeah.
That's fine and good, but I've always wondered why there is no definition of hyperbolicity for graphs. And of course, this is a justification for that. But I mean, you could also try to make a much weaker definition, which is I'm only going to consider paths of length up to something related to the size of the graph. So it's like a truncated definition. And
But they said you
Then
won't
row
get
doesn't-
anything interesting.
No, I'm not saying it's uninteresting. I don't know. Like I think it can be interesting, but it's not the
it's a
thing I want
different
to.
story.
I want to go back to my story because like hyperbolicity is completely interesting and we'll come back to it today, but I want to talk about cohomology with permutation coefficients today. So somehow I recall the things we've done last time. I hope you remember. Yes, Ken?
Okay, my second question.
Yeah, perfect. Yes. We always
So-
have good questions, so.
Okay, so this is it fair that I consider this Van Kalfen diagram, the disk, as some simple closed area that can be contracted, and the link between them are like somehow you join two closed like contractible contours that are simple by some like just by also a.
You're trying to understand why contraction in this sense is exactly the Van Kampen
Yes.
diagram.
Yes.
So I think it's clear that you can, triangulation of the disks means that you can contract each disk.
Yes.
And now you're left with a tree and clearly you can contract every tree, right? To a
Yes.
point.
Is
So
that
that's like, and you can show that essentially this is the only way of contracting things.
Okay, I just
like
want to
that's,
check that.
yeah, that's like enough. This is the structure of any like simplicial contraction.
But you don't have a good notion of an area inside
Yes.
the complex,
Yes,
right? You
yes.
don't see it's not surface in general.
Yes.
Yeah, this is a combinatorial object, so that's the way I count like area. Okay, great. So let's do cohomology with permutation coefficients. So last time we talked about the coefficient group being just 0, 1, F2. Today I'm going to talk about permutation coefficients. And if you remember, I said at some point last time that when you talk about F2, you don't care about orientation of edges and triangles. But once you start talking about non-characteristic to groups where not every element is the inverse of itself, you need to care about orientations. So what do I mean by orientations? So when I say the oriented edges, I mean every edge here is like the set XY, right? And then there are two orientations, XY and YX. Okay, and what do I mean by that? I mean this arrow and this arrow. Okay, when I write XY, I mean this oriented edge. And when I write YX, I mean this oriented edge. And similar with triangles, there are 6 orientations. So for every triangle, so usually people think there are only 2, and sometimes it's enough to discuss only 2, but in my case, it's important also to say what is the starting, think about it like a contractible path. I care about its starting point also. So there are 6 orientations, So it's x, y, z, x, z, y, etc., 6 of them. And when I say x, y, z, I mean, okay, there are the three points. I mean, go from x to y first, then from y to z, and then go back from z back to x. And notice that x, y, z, and x, z, y are the opposite of each other. Okay, so like if you reverse the orientation, instead of going clockwise, you go anti-clockwise. This is the anti-clockwise version of this. So we will just use the notation xy bar is yx. So if you reverse the edge, you get yx, and xyz bar is xzy. So if you went clockwise, you will go anti-clockwise and vice versa. Great, so I needed this. Now I need to also define to you a collection, which is not a single group, but a union of infinitely many groups. So for me, sim will be the disjoint union of the permutation groups acting on n elements for any n larger or equal to 2. Okay, so all possible finite permutations appear in this set. And on this set, there is a natural metric, which is the Hamming metric with errors. So let me recall to you what it is. So if sigma is in sim n, and tau is in sim capital N, and let's just assume that capital N is larger or equal to lowercase n, you can define the Hamming distance with errors between sigma and tau to be 1 minus n in the capital N in the denominator, all i's, all indices between 1 and the lowercase n, the smaller one, for which sigma I and tau I agree. So it's the complement of the proportion of indices on which they agree. And if you just think, okay, so let's just think as computer scientists for a moment. If you just think of any function getting a wrong input as outputting an error sign, okay, and an error sign is not a natural number, then this is exactly the probability that you sample an index out of the bigger set that sigma I disagrees with tau I. Because for every index larger than lowercase n, this will give me an error sign, and an error sign is never a natural number. And this is why it's called sometimes the Hamming distance with errors. Right, so this one has a metric. Did I want to say anything else before I dive into the cochains? So, okay, maybe before I proceed, I will just say something. I'm going to give you lots of technical definitions now, which are, you will see, just generalization of the cohomology we saw last time. And I'm going to motivate it only afterwards. Okay, so I'm kind of going to define lots of things now. The motivation will come 5 minutes from now. Great, so another notation, just the norm of sigma is the distance from sigma to the identity permutation, and the identity permutation on the same set, okay? Because notice that different identity permutations have non-zero distance between them, so you need to choose the correct one. The correct one is the one that acts on the same space, okay? Now I can define the cochains. So what are the I cochains? So now I'm going to use the correct notation. Sorry, last time I did it with the subscript. Today I'll do it with the superscript. So what are the I cochains? So this is the I cochains of X with permutation coefficients, and I denote it like this without any parameter here, like I do it like up there. And usually I just denote it by Ci. This is all functions from the oriented I cells to sim n, and here I'm using some n. So you send all oriented I cells to a specific permutation group, not to sim in total, so it has a specific thing it acts on, such that n is any natural number, so I don't restrict you which sim you choose here, but once you choose a sim, you need to send all of them to the same one. And if I is larger or equal to 1, so notice there is no orientation of vertices and no orientation of empty sets. Okay, so Only when I is larger or equal to 1, we want some anti-symmetric condition. Okay, so the function, if you evaluate it on an edge in this direction, it's the inverse of evaluating it in the other direction. Okay, so just an anti-symmetry thing, which says that f of a cell alpha, if you take the inverse orientation of alpha, it's the image of alpha inverted. Okay, so again, we saw that this is the inversion of this, and this is the inversion of this. Let me understand what do I mean by inversion. So these are the I cochains. And notice that we lost all linear algebraic structures. Right? Last time, this already was a vector space when this was, the target was F2. This is no longer a vector space. This is not even a group. Like you cannot take the product of two of these. Like you lose lots of algebraic structure, but we see this is an interesting object on its own. You still have the coboundary operators, and that's the important thing for us. So what would be delta I? It's again from Ci to Ci plus 1. And let's just write them down again. So delta minus 1 f of a vertex is just f of the empty set. So again, like we started from just something that associates to an empty set, a permutation, you just write it down on all possible vertices. What was delta 0 of xy? So notice now this is an oriented thing. And this will be f of x inverse f of y. And check that indeed f of x inverse f of y is the inverse of f of y inverse f of x, right? So that's okay, it's an anti-symmetric. The image is actually in C1. And lastly, delta 1 of f x, y, z is again just f of xy, f of yz, f of zx. So I go around the triangle according to the orientation, and I just take the product of the correct orientation of edges when I go over. So that's the delta 1 of f x, y, z.
Michael, can you do just two orientations and define everything up to conjugacy, or it doesn't work?
So it does work. You can also force all the x, y, z's to be conjugate to one another, and it doesn't change the theory because we don't really think about C2. We only think about the coboundary of C1 elements. Okay, so we actually only care about like the elements in C2 that are in the coboundaries of C2 in C2. Okay, so it won't really change anything if I add, like, for example, the conjugacy condition or something like that, but I don't really need it. Everything will be well defined without it. Okay, great. So now we can still talk about, if you remember, I coboundaries and I cocycles. So what would be BI? Would be the image of delta I minus 1, right? And you can check that this is again like what happened last time is that delta I composed with delta I minus 1 was the zero function, and here I write identity. And it should be understood that I don't mean this is the constant identity function, but whatever you plug in, it acts on a specific space, 1 up to n, and this would be identity of this specific space. Okay, so it's not generally a function, but still you can just define the kernel of such a map to be all those that are sent to some constant identity function on some size of space. So this BI, because of this condition, this BI, which is the image of these, is also contained in CI, which is the kernel. And again, it's a bit of a bad notation calling it a kernel, but I hope you understand what do I mean by that. Those that are sent to constant identity functions.
The identity, the inverse image.
Of all possible identities, the inverse image of all possible identities, and there are infinitely many, right? Those that act on 2 elements, those that act on 3 elements, and so on and so forth. Yes?
Saying that you could have defined this separately for every sim n.
No, I don't want to get, you're right, this is like, there are different ways of doing the same thing. You can define for every non-abelian group, gamma, just plug it here.
No, you need for every n differently. I mean, separate.
Yeah, I'm saying, and then you can take unions of these, and this is essentially a disjoint union of all CIX sim n with a specific n. That's what I'm doing here. I don't want to, like, I feel like those that don't know this theory, I'm giving them something that they can grasp, and those that know that there are other ways of doing it. That's great for me.
Calling this kernel and saying like it's like a kernel, so where
It's the union of kernels in
union
actual.
of the kernels if you actually take a group inside there and not this.
Yeah, you're right. Yeah, that's true. But still, like I lost the group structure when I did this, and I want to emphasize it because I did. Great. So this is still well defined. And these are the coboundaries and these are cycles. And again, I'll give you motivation just in a moment, so bear with me. I just want to define two more things. One of them is a metric on these guys. So we have a metric on permutations. Let's take it. Okay, so actually, whenever you have a metric space, right, you can take distance between functions to this metric space, just some on expectation, right? Like an L1 type of distance, and that's what I'm going to do. So I'm going to assume that your simplicial complex has measures, probability measures on it. Okay, so there's some mu2 here and mu1 here and mu0 here. Okay. So you can sample a triangle according to this distribution. You can sample an edge according to this distribution. Actually, this is on oriented stuff. So these distributions are on oriented elements. And then you can just define the distance between two cochains. So this is just the L1 distance between them. To be the expectation when you sample a cell according to mu I, an oriented cell according to mu I, of the Hamming distance of f of this cell compared to g of this cell. Okay, so the usual L1 distance of functions. So now that's great. The CIs have a metric on them, right? Once I fix these probability distributions. And then they have a norm. So again, the norm of the function would just be the distance from the identity, the constant identity. And again, you need to choose the appropriate identity. And now I can define, okay, and you have a distance from a set. What does that mean? A distance of a function from a set of functions is just the minimum out of all possible. So the infimum over all g's in A of the distance between f and g. Okay. So we have all of these notions. Now I can define the Chigger constant. So if you remember last week, we had the Chigger constant, and now I can, we had this Fn, if you remember, like in the Lineal Meshulam paper, they chose for every equivalence class, the function with the minimal norm, if you remember, the minimal Hamming weight. That's what we've done last time, and I called it curly F, like calligraphic F. And now I'll do it a bit differently, okay? But it's equivalent. So the cocycle Chigger constant, which I denote by HI of the complex with permutation coefficients, is the infimum over all F's that are cochains but not cocycles, okay, of the norm of delta of F divided by the distance from F to the I cocycles. And let's just unpack this for a moment. This tells you, so if this number is positive, this tells you that if your coboundary is small, you're close to being a cocycle. So my first motivation for this definition will be a property testing type of situation. which is due to Irit and Roy Meshulam, about covering spaces. Okay, so actually you should think of this parameter as somehow telling you how good is some specific tester is to reveal something. What is the tester? The tester says, okay, what is the weight of this thing? So, like if this is small, most of the triangles that you will check will give you 0, right? But this tells you that you are close to something which actually gives you 0 on all possible triangles, right? In my case, identity. Right? So it's in the spirit already of like property testing, and that will be my first motivation. So I'll try to keep on the board all of these things, and I'll try to use only like the 3 rubricas that I have there.
You can add also that for people who know how the normal trigger constant is defined, it's just a boundary is really the size of the cut in the graph, and the denominator is the minimum between the set size and its complement.
So notice that Avi's remark is great, because notice that when essentially this is well defined only for 0 and 1 in my case. And the 0 case is again the usual Chigel constant. That's essentially what Avi is saying. But actually it's a bit more complicated, right? Because here you have permutation coefficients. So instead of a cut of one side, you have n factorial many possible sides to the cut. And that's okay. Just like, it just makes it worse, right? The best thing is to cut the graph only to 2 parts and not to more parts, right?
2 factorial is still 2, so if...
Yeah, exactly. Yeah, so the sim2, like when you focus only on sim2, this is exactly the usual edge expansion parameter of a graph, and I'll come back to it actually. So at some point I'll need to recall what is the edge expansion parameter of a graph. I'll just quickly recall it, and it's equivalent to this definition when I is 0. Yes.
But your x1 is a complete graph.
In the linear Meshulam case, yes.
Yeah,
But my links won't. Okay, so that's a good question. My links won't be complete graphs. So you will see at some point, I will start arguing something about the links of a vertex. And the link of a vertex depends on how many triangles, the edges in the link are exactly triangles that sit on this vertex. So at some point, I will care about expansion in regular graphs, not regular in the, okay, normal graphs.
Yeah, but I mean,
or old-fashioned graphs.
The standard trigger is constant here will be.
Okay. You say that my point is that you can take X not to be on the complete graph. For example, you can take X to be any simple graph. Any simple graph is a simplicial complex. And then the one case will not be interesting because you don't have triangles at all. So everything is 0 here. And then, okay, that's not interesting. But the 0, 1 is interesting.
Yes.
And it's the usual edge expansion parameter of the graph.
Yes. So
that's what I'm saying.
In your case, H0 is not interesting.
In the case where you take a linear Meshulam complex, the underlying graph is complete, and then H0 is just a constant, right? It's like, I don't know, 1 or something. Like if you normalize it appropriately, it should be 1. Other remarks? No? Okay, great. So let's now motivate. So we want some motivation. Didn't do it correctly, right? I should. Okay. So I'm sure most of you care about random graphs, okay? Like just some models for random graphs. And maybe one of the most famous models for random graphs is the following. You take some underlying graph. In my case, just take 3. Maybe I'll put them lower. I'll just take 3 vertices. And you just take, for example, the loop around them. And how do you take a random graph out of it? You just write permutations on the edges, right? For example, let's take the permutation that swaps 1 and 2 here, the permutation that swaps 2 and 3 here, and the permutation that swaps 1 and 2 here again. And now let's just write up 3 vertices above every vertex in the underlying graph, because this acts on 3 elements. And now let's give them names. So this is the lowest, so let's call it 1, that's 2, that's 3, that's 1, that's 2, that's 3, that's 1, that's 2, that's 3. And now I have the rules of how to connect them, okay? 1, 2, swap 1 and 2. Great, let's swap 1 and 2, 3 connects to itself. And then I have the rules here, 2 and 3, right? Swap 2 and 3, and 1 to itself. And lastly, 1 and 2, swap 1 and 2, connect 3 to itself. Great, so on the level of graphs, whenever you write permutations on the edges, it defines you a covering graph. These are sometimes called lifts, and it's a very bad name because in topology, lifting a path has a very different type of definition, but this is on the correct way of calling it is a covering space. So this is just a covering graph of the underlying graph, and it generates a random model, but just taking these permutations to be random of larger and larger sizes, right? Just uniformly random, for example, for larger and larger sizes. So this is well studied, but we are in the two-dimensional simplicial case, right? And in the two-dimensional simplicial case, for example, here, maybe the triangle appears in the middle. And now you can ask yourself, can you, and now the word lift is a good word, lift this triangle up? And if you can lift it, in how many places can you lift it? Okay, so let's look here. You see that 2, 1, 1 is a triangle, great? So if I want to lift this vertex here, I can fill up the triangle. But if you check, the other one is a path of length 6. So I cannot lift the other triangle. Now, how do you see that you can lift the triangle only to one place and not to all 3 possible? Like a priori, you could have lifted it 3 times, right? Maybe there's a triangle starting from 1, a triangle starting from 2, and a triangle starting from 3, right? But the way you can see that this is not possible is just, what is the coboundary of this thing? So the coboundary of this triangle is 1, 2 times 2, 3 times 1, 2, which is the swap 1, 3. And the norm of this is 2/3. So the norm of the coboundary of the one cochain that you started with measures what is the proportion of triangles that I cannot lift. Okay? And this gives you a way of asking, okay, like, is your covering graph actually close to what's calling a covering space of the two-dimensional simplicial complex, in which case you need to lift up all possible triangles. So if you can lift up all possible triangles, it's called the covering space of the two-dimensional simplicial complex. And what we saw now is that one cochains give finite covering spaces of the one skeleton, while one cocycles give a finite covering spaces, blah, 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 of the two-dimensional simplicial complex. And you can ask the property testing problem, okay, if this number is small, this means that you can lift up most of your triangles, right? Does it mean that you can just change a small amount of the edges upstairs and now you can lift up all the triangles? So that's the property testing problem underlying here. And I will say that, again, like this is due to Meshulam and Dinur and Meshulam, but they count things a bit differently. So you can define my tester. My tester is lift to a specific point and ask whether you can fill up the triangle. But you can also ask the question, okay, choose a random vertex here and ask, can you lift up all possible triangles? Okay, and this is a different tester. So they studied this tester, and in my work with Alex Lubotsky, we discussed this tester. So you can see like, and the main difference is, what is this metric? Like I'm using the Hamming metric on permutations. You can use different metrics. Yeah, different metrics. Okay, but that's one motivation. So this is just an interesting topic, which this, like all these definitions just pop up when you try to study this thing. My other motivation is completely from group theory. So let me give you a few definitions. So my first definition is, and now I actually just erased what it means to be contractible, but I hope you all remember what it means to be contractible and what it means to be non-contractible. A simplicial complex X is residually finite if every gamma with infinite area, or every gamma that doesn't have a Van Kampen diagram with such a circumference. Residually finite will mean I want a finite witness for this. So we had this discussion before that like all this shenanigans actually tell you something about an infinite object. Can you give me a finite thing that will show me that although this path is closed, it is not, you cannot triangulate it. So how would you do that? What is the operative way of doing it? Give me a finite cover for which when you try, so notice that, let's look at this path, okay, of length 3. If I lift it up to 1, I don't end up in the same vertex. So you will walk 1, 2, 3, okay? You started here, you ended up here. Okay, so this already shows you that you cannot fill up the triangle. So this is a witness that this path, okay, so here it was contractible because there was the triangle there. But in general, if a path is non-contractible, you can find the finite covering space which witnesses this. Okay? So this is actually not a good example, but because this is not the covering space of the two-dimensional simplicial complex. But the whole point is that if you're not contractible, and you're residually finite, you will find some covering space that witnesses it.
How does it witness?
So I'll write down the definition, the formal definition, but I'll try to now. That was like a heuristic. Let me just write it down. So there exists a one cocycle f such that the norm of f of gamma, and I didn't even define what f of gamma is 1. Okay, so let's think about it. F is defined only on edges, but clearly it extends to paths, right? So what is f of a path? It's f of the first edge times f of the second edge times f of the third edge, right? So f of gamma, if gamma was x1, x2, x3, up to xl, it doesn't even have to be closed, but I care only about closed paths in this definition. What is f of this? It's f of x1, x2 times f of x2, x3, etc. Okay, we understand what it should be written here. This is a permutation. You can measure its norm, and it needs to be 1. What does it tell you? It tells you that, okay, for example, in the so let's look at the torus. For example, you can take this path, and we know it's not contractible, but it's still a closed path. The whole point is that you can lift it up to some covering space of the torus, which is actually, again, the torus, but somehow, maybe I'll do it with a cycle and not the torus, because it's even easier. So let's just take the graph, which has a single vertex and a single edge going that way. This closed path is clearly has infinite area because I have no triangles, I cannot triangulate it. But you want to show me that it's actually non-trivial. So what you do? You will, for example, write the permutation 1, 2 above, and then you have 2 vertices, and 1, 2 tells you, okay, you do this once and you do this twice, and this is a covering space of this, okay, by my definition of a covering space. And now you can see that walking on this path, when you try to lift it up, and again, this is the correct way of saying lifting, you end up either with this path or with this path, and these are not closed paths. So it's a witness that it could not be triangulated, because think about it. If this is a one cocycle and it preserves all possible triangles, if it had a triangulation here, it must have a triangulation here. So the fact that I'm using the word one cocycle means that it's a covering space on the level of two-dimensional simplicial complexes. And it means that it preserves triangulations.
Can you explain this for the definition?
Okay, so let me
Why-
say it in the group theoretic way. Covering spaces are subgroups.
No, you define it cocycle. Now, why you said that one cocycle is what you said about.
One cocycle is a covering space of two-dimensional simplicial complexes. That's just because you can lift all possible triangles and
Let's stay with the way
Yeah.
you defined it. So if you're a one cocycle and you start downstairs from a triangle, all three,
like this is not a one cocycle
what would make?
because delta F is 2/3 and not
What would
zero.
make it a one cocycle?
If it would be three disjoint
The
triangles.
only way it could be a one cocycle if the triangle.
Three
is
disjoint
a
triangles.
Three disjoint triangles.
And just because the cocycles of this, you can check that the cocycles of this simplicial complex are just those that are trivial, but you can do something, right? It's three disjoint triangles, but you can enumerate the vertices differently. You call, for example, here we saw that 2, 1, 1 was a triangle, right? So maybe you can call this triangle 2, 1, 3.
Wait.
Three.
A cocycle again. I'm thinking.
Yeah,
Can
you're
you go-
going too fast. Please slow down.
A cocycle by definition.
It's just permutation on the edges that when you take their delta, you get 0. Like identity,
You get
the constant identity,
On every
which is the
triangle.
same as the norm being 0.
Which means.
Yeah, all triangles have delta F is equal to 0.
Is identity, which means in the cover picture, that you go back to where you started. So if you started at a 1, you go along the 3 edges, you get back to 1,
Yes.
meaning you got a triangle. If you started at 2, you land back at 2, and if you start at 3, you land back at 3. So you get 3 different triangles. That's the equivalent to being a one cocycle.
Yes, but I'm just, my remark was,
That you will return to 1, 2, and 3.
No.
The triangle.
Yeah, where you go
Yeah.
through can differ, but you must.
It does not mean that there are identities on the edges. It-
yeah, so that was my second remark.
Only the
Doesn't mean,
product.
right, exactly.
So Irit said a very important remark, which is like, all this covering space thing says, lifting all the triangles exactly means that, okay, if you lift it here, you get back to yourself. It's equivalent to, if you start here and you walk, the walk associated with it, you go back to yourself in all possible cases. That's what it means to be a cocycle, which is the same thing as being able to paste a triangle in all these places, right?
So covering space and cocycles is the same thing here.
Yes,
Oh.
yeah, like I defined everything such that a finite covering space is equivalent to a one cocycle.
Yeah, but maybe it's also worthwhile to say, suppose you had a longer path, like two adjacent triangles. You had a path that was triangulated, for example, by 2 triangles. And then you think of any one cocycle, that path, when you look at it upstairs, it will always be able to be triangulated by 2 triangles.
You can lift triangulations. Actually, that's like, again, in topology, this is sometimes called the lifting lemma. If you open up Hatcher, like the famous algebraic topology book, it's called the lifting lemma in Hatcher, that if you have triangulation downstairs and you have a covering space, you can lift it up. Okay, great. So we had this discussion. My last remark, and this is what Avi just mentioned, is that, okay, for sure, if you want to be able to lift this triangle up, you must have this picture. But my point is that maybe this picture is like a permutation of this picture. What do I mean by that? You don't need to give the vertices the same names. So also here, I called it 1, 2, and 3, but you could have called them 1, 3, and 2. You will have the same picture, but it will change the permutations that you write down on the edges. So there is some equivalence relation on the one cocycle, on the one cochains, which is induced by just permuting the names of the vertices above. Right? The covering space will be the same covering space, but you can permute the names of the vertices. That will be important for me. Actually, that is exactly the fact that the 0 cochains, so this just says that the 0 cochains, which are just permutations on the vertices, act naturally on the one cochains. So they change the names of the one cochains in a way that doesn't change actually the covering space. So that's another remark that I will need later. So just keep it in mind. But at least for us, what does this say? This says exactly that a one cocycle is a covering space of the two-dimensional simplicial complex, and the fact that f of gamma, the norm is 1, means that no matter how you lift this path, it will be open now. It will not be closed, no matter how you lift it.
Don't you have to have just one place where you can close it?
Yeah.
For residually finite, yes, but this is equivalent to the usual definition of residual finiteness. And I'm going to define what a suffix simplicial complex is in a moment, and you will see that a suffix simplicial complex is a relaxation of this property and not the usual definition. Okay,
So could you
but this is
find-
completely equivalent because of Cayley's theorem. Yes.
So you are saying the definition equals to y is like a equivalent to larger than 0, is it?
So yeah. If you took any positive here, it's enough to be a witness, right? You agree with me that actually every positive here would be enough for a witness.
Yes.
But the one is good because we're going to now define another definition. This is just a warm-up for me, for another definition called being a suffix simplicial complex. And you will see that the suffix notion relaxes this and doesn't relax the just bigger than 0. Somehow, if you took here just larger than 0, and you'll try to generalize it in the way that I'm going to generalize it, it becomes not an interesting definition. Okay? But this is completely equivalent to the usual residually finite.
Why the existence of such one cochain implies that A gamma is infinite?
Like my claim is that whenever A gamma is finite, the norm of f of gamma is 0. That's an exercise. Like for every one cocycle, that's very important. The word cocycle here, not for every one cochain. Whenever you take a one cocycle f, and you take gamma, which has finite area, f of gamma is just a constant identity function.
Yeah, because you can lift the triangulation.
Yeah, exactly.
Yeah, but you are saying like this is not if and only if.
What is not? It is an if and only.
No,
It's not an if and only. Of course, it's not. Even here, you see it.
No.
Like,
Not every group is finite individual. That's what really finite. I mean. This is what he means. There are groups where it's not true.
Sometimes you
No. I don't understand. Okay. This property is a property of a simplicial complex. It needs to be whole. No, your time, please. Let me manage it. X is a two-dimensional simplicial complex. I'm defining what it means for it to be residually finite. It's a property that needs to be done for every possible infinite area closed path. Like for any infinite area closed path, you need to have such a covering. Otherwise, you're not residually finite. So what is to show a negation of residual finiteness? It's enough to find some simplicial complex, for a specific simplicial complex, being not residually finite, you just need one closed path whose area is infinite, but in all finite covering spaces, it's still always closed. That's the property of being not residually finite. But to be residually finite, you need to satisfy it for all possible paths. Okay. And I will just say this is a very well-studied, well-known group theoretic notion of residual finiteness. Okay, so I didn't just take it out of my sleeve, this definition. This is a well-studied notion. And let me give you a second definition, which is due to Gromov and Weiss. So,
You want to give us the number of simplicial complex that's not residually
do I want? So
I mean,
let me tell you that you can. I can do it for a CW complex. Is it okay for you? Like instead of having the underlying graph will not be simple graph, and you're not allowed to only paste triangles. You're not allowed to paste polygons instead of the cells being so. You start with just two loops. One of them you call X, the other you call Y, and you paste. Let's think. So x, y squared, x inverse, y to the -3. So how many?
Yeah, can we draw it?
Yeah. No, I can draw. So let's just count 3 + 1 + 2 + 1, 7. So you paste the 7 gone, such that the first edge of the 7 goes in this direction on x. The second and third go in this direction of y. The fourth goes against this direction in x. And lastly, the 3 last edges go in loops against this. So you paste the 7 gone according to these rules, you get something which is not a simplicial complex anymore. It's called the CW complex, but
But you can triangulate, right?
You can
triangulate
triangulate
it
the
in the
you
end.
can triangulate, but I don't want to triangulate it.
Okay.
Like, I guarantee you
Maybe
that,
Bobby
that you
has
can
this-
actually find a simplicial complex that has the same property, but the whole point is that this is not residually fine. So this doesn't satisfy this, and I won't show it. I won't prove it.
The loop is this loop.
Yeah. This is a closed, this is clear. No, actually the loop is Y.
The loop is one.
Yeah, the loop is Y. So
And how do
you
you
can,
prove that it's not residually finite?
so you can show that in every finite group, you cannot conjugate y squared to y cubed. How does it work? Like there is a like you cannot conjugate y squared to y cubed.
But you can do it in the group, in the mother group.
Yeah, but just by definition, this is the relation defined. Like there is an infinite group that has this property, but no finite
I was
groups.
saying, this says that y to the 3 is.
This is
conjugate
y3 is
to the
equal
two.
to x y squared x inverse. So you conjugate
But
y
this
squared to
relation
y3.
never holds down.
In a finite group, yeah.
Okay.
Yeah. It can only hold if y is the identity element, but that's the whole point. Y is not the identity element in the mother group. It is the identity element in every finite covering space.
It only needs to be of infinite order. Why?
There is some argument. You can show that this just never happens in a finite group unless y is the identity element. Yeah, like that's it should be a simple argument. I won't do it now, but it could be a simple argument. But again, you're taking me like to different places. So we saw something which is not residually finite, and the torus, for example, is residually finite. Okay. Gromov and Weiss relaxed this notion. Okay, because of things in dynamics and like ergodic theory, like their motivation was completely not these type of things, but they define the following: X is sofic. Is sofic, and I'll say just one word about this word. If you remove this C, this sounds like the Hebrew word for finite. Sofi is just the Hebrew word for finite, and that's the definition of Benji Weiss. And he thought that there were too many finite stuff in mathematics, so he decided just to use the Hebrew word.
Like Aleph.
Yeah, like Aleph in Cantor's work. Yeah, that's true. You need new notation, you need new words. Finite is overused.
Definition.
So, like, you always hear linear stuff, right? Like, if you add another definition with the word linear, it's like you're overwhelming the everyone. So he just uses the word sofic instead. So this is like a finite property which relaxes residual finiteness. And again, here instead of if for every gamma which has infinite area, and for every epsilon larger than 0, there exists a one cochain F. So now I don't require a one cocycle. That's very important for me. But I will require something about this one cochain F. So here I require that this F is a one cocycle. Being a one cocycle is the same as saying that delta F is 0. Is the norm of delta F is 0. So relaxing it will say such that the norm of delta F is smaller than epsilon, but the image of F gamma, the norm of this is larger than 1 minus epsilon. So somehow it's a one cochain. It's not an actual covering space, but let's call things with small norm here an almost cover. So you have better and better almost covers that almost always show you that this path is non-trivial. So I hope you see that the case epsilon is equal to 0 is exactly residual finiteness. So this is a relaxation of this concept. So whenever you're residual finite, you're automatically satisfying this because you can just take epsilon to be 0 on the spot. Yeah. Okay, great. This is just a definition. But the fact that this is a definition doesn't help us. So this is a motivation part. I'm sorry, I'm just dropping definitions on you in the motivation part. Just a moment, Kevin. I will just say, what I'm going to say now is the real motivation. Like I gave you two definitions. Now I want to give you two major open problems in group theory.
So,
Okay.
but there the F, it's really a sequence F epsilon, right? Because you need the.
So I wrote it in a non-sequential way, but you're right that if I take a sequence of epsilon tending to 0, I get a sequential definition. So if for every sequence of positive numbers that tends to 0, you have this f of epsilon for every.
Yeah,
like you can
the permutations in the question are growing.
Not necessarily. If you're residually finite, you don't have to grow.
No, in this definition. Yeah.
In this definition, if you're so
when
let's say
you
differently, if you're
longer-
sophic. Okay, so if you're sophic and not residually finite, you must have larger and larger ends here, using larger and larger. It must be sequential in some sense, but in this case, for every gamma, you can have a single f, not a sequence of f. Yes.
So the quantifier on gamma is
For
now.
every gamma and for every epsilon.
No, I mean, don't you need a gamma to be infinite? There.
I tried to write infinite and I wrote something wrong. You're right. Of course.
Okay, this makes.
For every non-contractible path and every epsilon, you need to have these conditions. Yeah, sorry, I wrote something wrong. Okay, great, motivation. Let's go back. So open problems. So these are two major open problems in group theory. One, find a hyperbolic non-residual finite simplicial complex. So we just saw that the Baumschlag-Solitar group, like the CW complex that I defined just a moment ago, and that you can triangulate and stuff like that you can make it a simplicial complex. It is not residually finite, so it satisfies this condition, but believe me, it's also not hyperbolic. And it's completely open to find a simplicial complex that satisfies both the hyperbolicity condition, but does not satisfy this first definition here. And for the second one, find any non-sophic simplicial complex. Okay, so the Baumschlag-Solitar thing that I showed you actually does satisfy the second condition. And we don't know of any simplicial complex that does not satisfy the second condition. And then I will just stress, these are hugely like big open, like these are major open problems in group theory. Like if you solve either of these, you will be well known in the group theory community. I don't know how many people there are, like you won't be a celebrity on a huge level, but in this community you will be famous.
Why is this group theory?
So it's actually questions about the fundamental group. Remember that last time I discussed that the paths, the closed paths that start from a fixed point in your simplicial complex have a group structure. So actually all of these questions about simplicial complexes actually ask question about this group. So,
And for every group,
there is a
you can
simplicial
draw a
complex.
simplicial complex. So it's really a question about find any group that's not Sophie.
Yeah. Yes, so I formulated it such that it's a question about simplicial complexes, but actually you can formulate it such that it's a question about groups.
Or any intuition that this object should exist.
It would be very.
Yeah.
Yeah, okay, so let me. The history is a bit convoluted here, so I think group theorists quite fast, quite like, this was 2000, like this is after Gromov and Weiss, so I didn't write it, but this is from 99, it's two different papers, and this is from 2000. So they asked, okay, are all simplicial complexes Sophic? Like it was raised as a question. And I think quite quickly, at least in the group theory community, people thought that this should be false. Like there should be non-soft, like you should be able to find such an object. That's what group theorists thought. But actually in the probability theory community, there was a stronger conjecture that if true would imply that there is no non-Sophic, like that every simplicial complex is Sophic. So it was an interesting question in the sense that there were competing conjectures. One said that all groups should be Sophic. one said that probably there are non-Sophie groups, but actually me with some other guys like refuted the probability theory problem. So somehow now it's even more evidence that such an object should exist, but we don't know how to do it. Okay, great. Maybe I'll just state the thing that I actually wanted to show you today. So we just saw definitions up until now, but I wanted to show you a proof of something today, which is not the Hoffman-Kale packet that I promised. So I said last time that I want to talk about two papers, and one of them is my own with Yuval Peled from this year, so here, Chapman and Peled of 2025. And I have everything on the board. Remember, there is the Chigger constant. We know what is non-Sophie, and we know what does non-residually finite means. And we should remember in our head what is hyperbolic. It means that the area of a closed contractible curve is bounded by, in a linear way, by its length. So our theorem states the following. So let P be in the mid-range. So take P here. So P is between n to the minus 1/2 and I'll do it like this, and n to the minus 1, and I mean, okay, it's n to the minus 1 plus epsilon for epsilon between 0 and 1/2. That's what I actually mean. Then if y sampled according to the linear Meshulam model is asymptotically almost surely, so with probability tending to 1 when n tends to infinity, has h1 of y with permutation coefficients asymptotically growing faster than n to the minus 3 e to the minus 1. Okay, so let's think about it just for a moment. This tends to 0, so it's okay that your Chigger constant tends to 0, but if it tends to 0 in a way which is asymptotically better than this thing, then y is non-Sophic. And that's nice because we know that y is hyperbolic. We know that if you are residually finite, you are Sophic. So this, if for some reason this is true, this will resolve both of these problems simultaneously. Okay? And not only it will resolve it simultaneously, it will show you that just a random simplicial complex satisfies in the mid-range, satisfy all the things that you want. So it's very much in the spirit of, I don't know, the probabilistic method that actually you're looking for a hay in a haystack. So I'll stop here. I will say the next part, like the next 45 minutes after we'll take a break, or 40 minutes, I don't know. I will show you that this is actually a group theoretic generalization of the fact that expander codes are not locally testable. So the proof for this is just the non-local testability of expander codes, which is why I brought this whole series of talks. So I wanted to give you all these crazy definitions from topology just to show you a nice application of the non-local testability of expander codes. So that's like the next 40 minutes, and let's take a break for 6 minutes, say. Okay, let me say it differently. Since the definition of hyperbolic groups, which is like due to Gromov, like the things that I discussed last time, all the simplicial complexes that are hyperbolic, many things were shown to be true in the hyperbolic case that are not true for general. Algorithmically, for example, if you know, like there are undecidable problems about groups in general, many of them are completely decidable once you're hyperbolic. For example, the word problem.
For the polynomial times.
Yeah, right, like even the efficient algorithm. So it's somehow a very nice class.
I see.
And somehow no one was able, and we know many examples of non-residually finite things, but somehow no one was able to find like something which is hyperbolic and non-residually finite. Like people just say, okay, it's such a nice collection of groups, such a nice collection of complexes. Maybe hyperbolicity just implies this definition. Maybe people believed it at some point. I think today no one believes it, but still, maybe out of left field, someone will just prove it, right? Like it's always this case, right? Like there is some conjecture, maybe everyone thinks one way, and sometimes the truth is just in the other way, right? So we just don't know at this point whether you should believe that hyperbolicity implies this first definition, or should you find an example that not. And I think most people think that if you can find an example, it's out of these random objects, because these random objects are always hyperbolic. That's very good about them. But we will see in a moment, I will add another definition, which is called property tau. And somehow property tau tells you that you don't have many finite covers. And then if you're hyperbolic and you don't have many finite covers, maybe all the covers don't see the fact that this specific gamma has norm one, right? Like maybe they cannot make this thing open up in a finite manner. So somehow you will see there are some competing forces in these random things that some people are optimistic that they may resolve this first question. The second question is quite new, like is newer, and tackling it through random groups is a recent thing.
Like property tau, the connection between property tau and this non-residual finiteness, is this proven or is it just speculated?
No, it's not a matter of speculating. You will see that property tau is very similar to having positive, like good distance in your code. And you should think of these covers as code words. And it essentially tells you that the code words are very far apart from one another, which is the same as saying that there are not too many of them, right? Just if you packed and you can draw big balls around them that don't touch, then there are not many of them. And that's like essentially what property tau tells you, which just tells you that you don't have many covers. Like if you want to hope to have this first property, you want as many 1 cocycles as possible. But somehow property tau will tell you that you don't have many 1 cocycles in some rigorous manner. Okay, so that's I don't know, like
Also, there's some like analog of aeroplane codes.
there's a natural analog of distance between these covering spaces. It's what is property tau, and I'll show it in a moment.
Let's get this. Each one's supposed to be a number between 0 and 1.
Or 0. Actually,
Yeah,
it's
so-
regarding what we discussed before. The torus has H1 0 on the spot, not positive. Although it's a finite object.
But
I wanted to
P
write it down
is
before.
constant. P is constant, then this is 1 over m cubed.
Yeah, P needs to be between 1 over square root n and 1 over n.
Yes, otherwise some other properties that I will need will not work. So I don't know how to do it. When P is constant, then pi1 is trivial.
Sorry, so P is.
Wait, I'll just say it. When P is constant, pi1 is trivial.
Oh,
And then this is bounded away from 0.
okay, sorry, yeah, okay. So P is between 1 over n.
Yeah, and 1 over n, yes. For example, it's enough to be omega of n to the minus 2, right? That's enough for.
What does it mean?
What does it mean? Like where this number comes from, we will see it's related to the number of triangles that I expect to have in the complex.
Wait,
Like if you have a stability rate better, like a Chigger constant better than 1 over the number of triangles, then you.
But what does that mean?
Yeah, I don't know. That's a good question. Like you want the intuition on this condition? I don't know. It just works out that when you do the error code type of proof, that's the parameter that you get. I'll show in a moment where it comes from. It comes from the proof for me, not like I don't have an intuition for this number. Yes.
why do we expect that? So some
I don't expect it. I didn't say that I expect this to be true. You're asking a very deep question. Like I don't know if the Chigger constant is bounded away from 0 for this.
So if we only look at like f in the definition being like just one, like the denominator is just making one arrow, then somehow I feel the h1 corresponding to that is like n to the minus 2 times p. Is that correct?
Why n to the minus 2?
It's like you fix one point and like you count the number of triangles involving this points, then that's n square.
So what did you say? Let's just say it
Maybe
again.
that's not okay. I'm missing some stuff.
Oh, maybe you're already
Expected
something.
thing. Like what do we expect for this H1?
Yeah, I don't know. Like, okay, maybe I should say I didn't say it during the talk, but we should resume anyway, right? Like,
Yeah, you can.
yeah. So let's resume. Hopefully, most people are here. Okay, so let me just say that for a fixed complex y, as opposed to the usual Chigger constant, which is positive whenever the y is connected, for example, there could be a simplicial complex for which this is 0 on the spot, even though you're a finite object. Let's see the example. The example is again the torus. So H1 of the torus with same coefficients is just 0. It's not like there's no asymptotics here. It's 0 on the spot. So here I'm not only assuming that.
Why?
What?
Why is it 0?
Yeah, actually that's not an easy exercise. Like
But you cannot
It
say
appears in a-
some homology invariant or something.
no. That's like a sequence of examples due to Becker and Moshayov. So this is Oren Becker and Jonathan Moshayov show that this is 0. Okay. So the stability rate of the torus is worse than linear. That's essentially what
Is
it
this
is.
the looping you did?
No. That's not like you need a clever. You need like a sequence of one cochains that have very small coboundary, but are still you need to change them very much to make them actual covering spaces. Right, like you need to change them very much to make them cocycles. That's just like you generate a sequence of things for which this is small and this is large. And
the
this
result
sequence
of-
just shows that this infimum is tending to 0.
The result of Lazarovich in this.
It's only on genus 2 and above.
Yeah, what does
And
it
it all-
say in this language?
Also 0.
Or, sorry.
All closed orientable surfaces has H1 0. Yeah, because in their case.
H10, yeah.
Yeah, the stability rate is worse than linear in their case as well. Probably worse than linear in their case as well. Other questions? So I'm just saying that like this is quite an optimistic assumption. Yeah, like the fact that I like this theorem is just it's related to these very famous open problems, and it uses a technique from theoretical computer science. So for me, that's the appealing part of the theorem. I'm not sure that this is I'm not very optimistic about this being true. That's my point. Okay, so
Any reason for that?
for this to be true or not be true, I just don't know. I have no intuition about the the first constant of these objects.
But maybe you can fix some typical F.
In our paper, I'll just say, in our paper, we also study the Chigger constant in these two regimes. But that's very easy because in this regime, the group is essentially free, and in this regime, the group is trivial. Okay, but still, you can ask questions about the Chigger constant of the simplicial complex, and it makes sense.
What is it?
So it's bounded away from 0, but in a way that seems to make this seems wrong. So in this direction, it starts from being constant and it tends to 0 from this side, and we can show that it tends to 0. Here we have only lower bounds. So our lower bound gets worse and worse when you get here, but we don't have an upper bound. We don't know to show that actually it tends to 0. But already from this side, it seems as if it just tends to 0. So I'm not optimistic that this is true, but still, I don't know.
But did you study it for specific F, like without taking the infimum?
What do you mean for
Like,
specific
example,
F? Yeah, I don't know even how to. Yeah, like it's very hard to understand any of these parameters in the case of a random complex. In the middle range. These two things are very mysterious to me in the middle range situation. Even for a single F, I don't know, like construct a natural sequence of Fs and start testing them. I just don't know.
Delta F you compute immediately. But the
It's a random
denominator,
complex. I don't know. What does you mean? I can run a simulation on the computer, but like.
you can compute the expected size, everything.
Yeah. Okay, that I agree.
But the denominator, it's a distance from some set, that's harder.
And this is a very structured set. Yeah, right. You always know, the only thing that you essentially know usually is that here you have the identity thing. Right? So you like measure norm of delta F to norm of F. Right? This is always smaller than delta F divided by the norm of F. But somehow, like, is this genuinely the closest thing in CI? You never know. That's kind of, it's an infinite search space. But like for every fixed simplicial complex, this is already an infinite search space. So somehow, I don't know, like maybe you do have like something interesting to simulate it or something. I don't know.
Okay, you want to?
Yeah, let me maybe, okay, final question and then I'll move on. Yes, no?
Yeah, can you clarify the theory? I mean, you have
This is asymptotic, then why is asymptotically almost surely?
but you actually need to get to have you need to work with the model of linear Meshulam. You can.
Yeah, actually, okay, so I will say that actually I will say two things. One of them is that we are not the first to prove such a theorem on some random model of groups. Alon Dogon did it before us, but he had some theorem that actually assumes less about this. So he doesn't need the Chigurh constant to be bounded away from zero. He needs, like, this is called linear rate of stability. He just needs any rate of stability. Okay, and I won't define that because that's out of the scope of this thing. And also he uses unitary coefficients and not permutation coefficients. So sometimes in a parallel world, we have a result by Dogon, which is similar, but it does not refute this thing. So the thing that he gets only give you a non-sophic object and not a non-sophic hyperbolic object. That's like the pros of our type of theorem. We assume more, so this is more than what Alon Dogon assumes, but we gain more, we resolve both of these problems simultaneously. So that's my first remark. Yes. And the second remark is that our proof method is so elementary that it essentially works on any random model of groups with any coefficient group. So you will see it is so kind of down to earth that actually you can use here unitaries, you can swap it with other families of groups, you can study property MF, so like if you care about like operator algebras and stuff, you can swap it same with unitaries with the operator norms on them instead of the Hilbert-Schmidt norm, and you get something called the MF property, and you will show that if this is true in this MF case, then our proof show that there is a non-MF group, which is again an open problem that I could have written there, but I don't want to. So like our proof method is genuinely so elementary that it's also generalizable to more cases.
But in this model, you can take any probability distribution on these complexes.
So it's not any probability distribution on these complexes. No, that's not what I'm saying.
Okay.
You will see at some point.
Let's see the elementary.
Yeah, let's see it.
Down to earth that we really want to see it.
Yes, that's true. We have half an hour. So let's try to do the proof sketch. I didn't do it during the mistake, but I just want to see how I want the rest. Okay, great. So, proof sketch. And the rest of the talk is the proof sketch, but let's start from a much easier thing. A matrix, an m by n matrix over 0, 1. It clearly defines a code, which is the kernel of A. And in this case, we call A a parity check matrix, right? Parity check matrix, this A, for this code C. Now I want to define something which is not very, people usually don't define it that way, but just bear with me. Let's call a parity check matrix.
Is the left or right kernel? Sorry.
This side sits in F to the N. So it's there. Like you multiply from the right, like A times V. is equal to 0. Yes, sorry. So A is called row testable if so let's write it that way. The norm of if for every v in f2 to the n there exists a w in the code such that the distance between w and v, and this is the normalized Hamming distance, V is not in the code. V is any vector. W must be in the code. That's very important. So the distance to the code is bounded away by rho times the norm of A times V. So the norm of A times V is just the proportion of parity checks that you do not satisfy, right? So if you satisfy most of the parity checks, you're close to the code. That's what it says. And the important thing is that's a property of the parity check matrix, not a property of the code. For every code, you can find a parity check matrix with very good rho. I think 2 is, or 1/2.
It's not, if you don't insist on a sparse.
Exactly. That's my point. Like for every code, you can find some parity check matrix which has this property, but usually it's not sparse. And the interesting case is the case where A is actually has constant weight of the rows, for example. Okay. The very sparse case. Okay, so now it's well known that if A it is a random n divided by 2 by n matrix, and when I say random, uniformly random 0, 1 in every entry, then C has rate, normalized rate, 1/2, and distance. So again, asymptotically, almost truly, when n tends to infinity, the rate is 1/2 just because this is an n over 2. Like I added half as the maximum number of constraints, and the distance of the code is larger than 1/10. Okay, by 1/10. But observation, A is omega n testable. So if you ask about the random parity check matrix and you ask about this property, it's as worse as it can get. Okay, so this row being on the order of this dimension is the worst that you can expect. Okay? So let's convince ourselves that this is true. Again, I'm sure that for most of you this is like completely clear, but let's do it. What do? You take your random parity check matrix A and you delete the last row. Okay? And when you delete the last row, you get another parity check matrix B. And asymptotically, almost truly, the kernel of B is strictly larger than the kernel of A. So you genuinely, when you took less constraints, you got more things, but still the distance of B is essentially as good as the distance of A. What does it tell you? It tells you that any element in B, which is not in the kernel of B, which is not in the kernel of A, is both very far away from the kernel of A, from the code, but it satisfies essentially all the constraints except for the last one. So like this norm is about 1/n/2, so it's 2/n, but this thing is constant. It's 1/10. Okay, so that's like very simple, and I'll say that in the locally testable case, because this is not local testability, actually for locally testable codes, the famous type of argument of this thing is with expander codes, where you locally change on one vertex just the local code, and like again, you satisfy most like the global, like the other parity checks, but not this specific local situation. You change it a bit, and a similar argument works there. So again, this is very famous. How do you apply it for the linear Meshulam complexes? Very easy. Sample a linear Meshulam complex and either add or remove one triangle. Okay? So I'm claiming that when you sample y according to the linear Meshulam model, and then just plug in the path 1, 2, 3. Okay, so z is y with the triangle 1, 2, 3. So almost surely y does not contain 1, 2, 3. Not only it doesn't contain 1, 2, 3, we saw that the area of 1, 2, 3 before I added it is almost surely infinity, right? Symptotically almost surely infinity. So what do we get from this? We get a pair which is very similar to the A and the B from before. Okay, so that's like the main idea of our proof. But now I need to show you that this actually gives you all these non-suffix stuff. Okay, so let's do that in a moment. To that end, I need to stop the proof sketch and define to you more things which are called property tau. Okay, and actually Alex Lubotsky was here almost a month ago, maybe a month ago already, and he gave a whole what is lecture on what is property tau. And I'm just gonna define it in a way which is easy for us.
So in the regime, the P that we're in, the complex is hyperbolic.
Yeah.
So the complex is hyperbolic. So what do we know about these both y and z? So in y, 1, 2, 3, the area of 1, 2, 3 is infinity in y, but clearly it's finite in z. So that is a main difference between y and z. Both of them are hyperbolic. Both are hyperbolic. Because if you think of it, sampling z in this way is almost the same as sampling according to the usual linear Meshulam model. Like it doesn't really change the model. So all the asymptotically almost surely things are there. And we can just, the way I'm going to do the proof sketch is that here I'm going to also without loss of, not without loss of generality, like assume by contradiction that y and z are also sophic. So assume by contradiction, assume by contradiction that y and z are sophic. Sophic and also, y and z are sophic and that h1 satisfies this condition for both of them. Right? So again, like I'm assuming something asymptotically almost surely, then it should happen both for y and for z. Asymptotically almost surely. Okay, so
What happens if Z is not, doesn't satisfy this assumption?
what do you mean? What happens if? This assumption, you could show that if this is true, then h1 of y and h1 of z satisfy this condition asymptotically almost surely. Because z essentially is sampled according to the same distribution. And because it's asymptotically almost surely, like some union bound type of argument automatically shows you that.
Okay.
Like you can do it. Like I'm mumbling something in a way that is not convincing, but you can do it.
Combining, like,
Yeah.
a priori, there is a case where Z.
It may be the case that this sampling method of z is such that it doesn't give you this condition. Yeah, that's true, but it's not the case here. Like,
I mean, you're assuming also that Z is not sophic, right? That Z is sophic, sorry. Right?
yes, like I don't care which one of them is sophic. Like my goal is to show that either y or z is sophic. So to show you that at least one of them is non-sophic, it's enough to show you that assume by contradiction that both of them are sophic, because even if one of them is non-sophic, I'm kind of done, right?
I mean, technically you wrote then Y is non-sophic. I mean, Z is never mentioned in the theorem statement. But
You're right, but my claim is that yeah, they're essentially identically distributed. Yeah. And you're right. There is some how do you say?
Subtlety.
Nuance, subtlety here that I'm kind of
no, I'm just
moving under the rug. But
understand if
my claim is that
Z is sophic or not, or Y.
so my point is kind of okay. Either Y or Z are sophic, in which case this proof is essentially done.
Then there exists a non-sophic.
Yeah, okay. Not that I don't want to write there exist. and non-sophic hyperbolic proof. That's my point. Okay, and which resolve these two things simultaneously. So let's assume just that, yeah, that at least that both of them are sophic, and if not, there exists some non-sophic hyperbolic. Yeah, that's what Avi just said. Okay, never mind. To finish the proof, I need another definition, which is the following: X has property tau if every one cocycle F which is connected. So what do I mean by a connected one cocycle? Think about it. A one cocycle defines a covering space. Its graph is either a connected graph or not a connected graph. And we saw both examples. Remember, we had this joint union of triangles. This is a non-connected case. And we can cook up connected cases, okay? So you restrict yourself only to those one cocycles which are connected. So if every one cocycle F which is connected is a row edge expander. So X has property tau with parameter rho, larger than 0, if every vertex set of size at most half the size of the vertices in every connected covering expands by at least rho. So the number of edges touching it is at least rho, the number of vertices in the set. Okay?
If you don't require the cocycle to be connected, you talk about like expansion in the connected component.
That's the same.
Oh,
You can just decompose every one cocycle to its connected component, and this claim is just each connected component is a rho expander individually. Yeah. My whole point is just that, yeah, like this connectedness is just restricted to the property of the connected components. And now let's say a few facts. First fact, and like before, remember how we used the distance of the code here. The way you use the distance of the code is that both the kernel of B also have good distance, right? And my point is that property tau is exactly the property of good distance in the context of these simplicial complexes. And this fact will explain to you how to see that. So the fact says the following. So if alpha and beta are one cocycles, then if and X is a property tau, and X has property tau, with parameter rho, then the distance of alpha and beta being small. Notice that we already have a notion of distance between cocycles. That's good for us. And what do you want to say? You want to say, okay, if two things are too close, for example, in the code, they are actually the same code word. This is exactly the claim that I'm going to write. If the distance between these cochains is less than rho over 2, it implies that alpha is the same as beta. And what do I mean the same? You can permute the names of the vertices of alpha and get back beta. So the equivalence relation that we said, as covering spaces, they are the same covering space. Okay? So I hope you already see that that's very similar to being distance in the code. So like having good distance in the code. Great.
The definition of distance involves some probability distribution.
Yeah, okay, that's a very good question. I didn't say it all, but my probability distribution is always the uniform distribution on the triangles. And then what is the distribution on the edges? It's choose a uniform triangle and choose uniformly an edge out of it. Then what is the distribution over vertices? Choose a uniform triangle, choose a uniform vertex out of it. So it always comes from the triangles, the distribution over edges and vertices.
But that's not uniform?
No, not because
See,
the graph is not regular.
isolated edge.
The edges are not regular in the number of triangles that are incident to them.
Oh, okay, but it's like
On the triangles, on the top faces, it's always uniform. But then, like an edge that is in many triangles has a higher probability of being chosen than an edge that is incident to less, like a fewer triangles.
yeah.
So you don't see isolated edges, but you don't have them in this regime.
Yeah, exactly. Indeed. It's supported only on non-isolated edges, for example. Thank you. Actually, that's a very important question and a very important clarification. Now, another fact, actually, this is a theorem. It's not good to call it a fact. This is due originally to Garland from 73. Afterwards, Zhuk have done great things with it, I think in 2002. And most recently, Oppenheim used it in 2018 or 19. And I think now the most common name, at least in the theoretical computer science community, to call it is the Oppenheim's trickling down theorem. And I won't give you an exact form of this theorem, but I'll just say the following thing. If X has if all the links of X, if all the links of X have good expansion properties, then X has property tau. Okay, so I'm not even giving you the exact parameter. So X must be connected himself, like it's not a union of disconnected, like it's not a disconnected simplicial complex, it's a connected simplicial complex. But once you have this, if all the vertex links in the two-dimensional case are very good expanders, then X has property tau, it satisfies this property. And this is a local to global type of argument, and Yotam has beautiful actually lecture notes about it that he gave in Simon's. So if you want to check like 4 pages that just give you all the details very clearly, very neatly, check Yotam's notes. So this one we need, now let's think about it. My claim is that in this regime, what is a link of a vertex? It's exactly an Erdős-Renyi graph. So the only missing piece to show that these y's have, that both y and z have property tau, is to convince yourself that in this regime, an Erdős-Renyi graph is a good expander. And this is a sequence of works. So I'll just write the names of the people who did it. So this is another theorem. This is originally due to Feredi and Komlosh from 81. Then Wu and Chang, Liu and Wu. From, I think this is 2003, this is 2005. I'm not sure how to say its name. Koja or Oglan. I'm not sure. From 2007. And finally, and that's what I wanted to, like, I originally thought that I would have enough time to actually show you the proof of this thing. And this is lastly Hoffman, Kale, and Paquette. If you remember, I said that I wanted to talk about their paper. Kale, Paquette. From 2021, so it's a long time until we got the optimal thing here. But what they proved is that in an Erdős-Renyi graph, once you are connected, you are a very good expander.
But you don't really need that. You have you allow epsilon in the exponent.
You're right, that's why I
You
said
don't
that.
need even the first one. It's a trivial counting argument.
Great, okay, so Avi says that you even don't need, I don't see it, like, I think you need a trace method, no? You don't need a trace
Now,
method?
if you have a graph of size n and the degree is n to the epsilon, then
Yeah.
it's an expander. We know it even if the degree was 3. You don't need any of this.
Ah, nice.
Yeah.
You said that at least in my parameter range,
Your
it's even easier, but my point is that this sequence that shows you that actually, even if I took, so in my arguments, I don't really need the exponent to be between n to the minus. So my theorem, like my point is that I could have taken here log n divided by n.
Yeah, and this will still be trivial.
No,
Yeah, degree log n will guarantee expansion.
that's trivial.
In a random.
Yeah, random graph, yeah. You just don't
Comes
need
out
isolated
isolated.
letters. Anyway, it doesn't matter.
Let's go
Continue.
No, I want to understand it. We are not agreeing on the same thing. I'm sure that this is non-trivial. The normalized Laplacian having a spectral gap of essentially 1 should not be trivial in this parameter range because they worked so hard on this. Like I really don't understand what I'm missing.
Let's not argue about
We
it.
can do it offline.
Yeah, we can do it offline. Like that's a good discussion, but let's do it offline. But it's good that everyone is convinced, and I don't need to say anymore. But I claim that up until recently, some questions of this form and getting actually
Yeah, some.
this actually about the normalized Laplacian, which is what you need here. Like getting this close to the connectivity bound, if I understand correctly, that was just
We
recently.
don't care about being close, so we want to see the.
Yeah, exactly. We want to see the proof, but essentially you all say, okay, that's obvious, perfect. I'm happy that you said that this is obvious. Let's finish the proof. So another fact, and that's really an easy fact. If H1 is positive, if your chicken is positive and you're sophic, then you are residually finite. So we had these two definitions. They're no longer on the board, but if the chicken constant is positive and you're sophic, you are residually finite. What does it tell you in the context of our y and z? Think about it. Being residually finite means that this path in y, there is some finite covering space of it where the norm of this path is 1. Okay, so there exists some one cochain f of y such that f of 1 to 3, the norm of f of 1 to 3 is 1. Great. The whole point is that, okay, f is not the one, sorry, one cocycle. The word cocycle is important. One cocycle of y such that this happens.
Wait, this is definition of residual finite, right?
The definition was for every gamma, and here I'm taking a specific gamma that we know it has infinite area, right?
But I mean, for sophic, you have epsilon. Like you don't, you are taking one.
So I use the fact that if H1 is positive, and we assume here, if you remember, I just said it out loud, that I'm assuming that H1 is like omega of n to the minus 3, e to the minus 1. In particular, it's non-zero, it's positive.
Yes.
Being positive, with no bound, just being positive, plus being sophic implies you're residually finite. This is a fact. I'm saying this is essentially an easy exercise.
Oh, you are proving this fact, or you...
No. I'm using this fact
Okay.
to say that moreover, like we assumed here only that they are sophic, but actually because we also assume that their H1 is bounded away from 0, we can assume that we get for free that they are residually finite.
Yes.
This fact. That's what I'm using. Sorry, I'm only using this fact for proving this fact. But this one cocycle, what do we know about that? The delta F, if you think about it in Z, like it satisfies all the triangles in Y. The only triangle that it doesn't satisfy in Z is the 1 to 3 one, right? So we know very well what is the norm of this. The norm of this is just 1 by number of triangles. Like this. Right? On the other hand, they have property tau, which exactly means, okay, so we know this. So the fact that H1 was omega of n to the minus 3, p to the minus 1, implies that there exists a one cocycle, a G of Z. Okay, it's not a one cocycle of Y, it's a stronger condition, it's a one cocycle of Z, such that the distance between F and G is bounded by what? So we need the definition of H1. So this is usually in the denominator. So this is 1 divided by H1 times this.
But this is at least one of the triangles. What?
It's equal to.
It's equal to.
It's at least. I mean, it's at most, but it's equal to. There's one triangle.
In this case, it's actually 1 divided by the number of the triangles in Z.
One
number of triangles of Z.
Okay,
like we generally know that this is
the only triangle
that is not satisfied and it's completely non-satisfied. So it's actually on the spot, but it's enough to show you less or equal. It's enough. Okay, so DFG is bounded by 1 over H1 times this thing, right? Delta Z of F. Do I need? Is it in the denominator or in the denominator?
No, it's like that.
Yes, like that. It's okay. Perfect. But this tends to 0 because this is a little omega. This tends to 0. Like this whole thing tends to 0 when n tends to infinity. But this contradicts property tau. Okay, why? Both F and G are 1 cocycles of Y, and Y has property tau. Because of this condition, they cannot be just changes of the names of the vertices of each other. So their distance must be bounded away by some constant. I don't know, like the constant parameter, you actually can write down the constant.
Because of what condition they cannot be?
Property tau.
Property tau.
No.
Property tau of what?
From the triangle being 1.
No way this triangle is open up in all of F and is closed up in all of G. And the difference between F and G is only permuting the names of the vertices because, yeah, that's what I need. So they must be far away from another. How far away? At least a constant away from one another. So this cannot tend to 0 contradiction. Okay, so that's our proof. Like
Did you use this fact?
We only assumed here that they are sophic and we deduced that they are also residually finite. Just because H1 is positive. H1 is positive implies that sophic implies residual finiteness. So somehow I'm winning by this.
So your H1 needs to be larger than number of triangles.
Yeah. That's the number. That's the expected number of triangles, right? Or 1 over, I don't know. 1 over the expected number of triangles.
Okay. Yes. Okay.
Maybe I wrote something here. Maybe it's, I don't know. Like something here is like maybe the other way around. I'm not sure. Because this needs to tend to 0, right? And
it's fine.
Yeah, this is
okay. If you're convinced, that's great. Yeah, I'm sorry. I'm too much on the board. I don't know. I think it's nice for computer scientists to see such a proof because that's like taking a bread and butter idea from computer science and applying it in this context.
What is the fact that it's 1 if it was 1 minus epsilon, it would 9?
Yeah, but I need it to be a 1 cocycle. That's very important for me. You're right that if I'm losing something here, yeah. This is the important parameter that is important. Otherwise, I cannot use property tau. Like property tau doesn't tell you anything about almost coverings. It tells you something only on coverings on the spot. So residual finiteness is the thing I need here for the argument to work.
Can you say
That's actually like I will say that I think one of the most interesting things in like all the study of sophic objects is kind of, do you have a notion of property tau that is for almost coverings, right? Like 2 almost coverings are either very far apart or are essentially like like essentially the same. Like you need some notion of this property towness for the almost things. Those that have.
Another question for graphs.
I don't know.
I guess you need some equivalence relation. Like I'm worried you take a cover and then you just slightly modify it in two different ways, and that gives you two almost covers that are close to each other, right?
Yeah. So again, I don't know if I even know how to like formulate it now, but I think what like the important. Like, Abby essentially asks, okay, why did I need this? This is not that important. Just the fact that it's positive is important for us. The only thing which is important is that I use here the word one cocycle. And the word one cocycle is important to me because property tau tells you only things about one cocycles and not on cochains with small coboundary. So somehow I'm saying maybe if you want to actually construct non-sophic objects, it's natural to try to develop a property towness type of property for almost coverings. But again, like, I don't know, it's not even clear how to formulate it. So
Can you see again like why it has property tau?
why it has property tau? Because of the Garland method. So Garland's method says that if the links are very good expanders, then you have property tau. And you said that this is trivial in my parameter range, so I don't even want to say anything. So this is just trivial for all of us. Yeah, I'm so bad at this stuff. So I needed to convince myself for a long time that all of this is
You're not bad. I don't think it's trivial in the sense that you want.
in the Laplacian. Yeah, that's what I think.
Depends on the definition of
If
trivial.
the degree is bigger than 100 log n, all the degrees are roughly of the same magnitude. And then
No. That's in that case you use Faraday cohomology. It's trivial. That's easy. That's an easy trace method. That I agree, but you don't have this guarantee on all links in the parameter range long.
union bound.
If log n divided by n, there are vertices of with constant degree.
Log n, no, 100 log n.
Not 100 log n. It's on the constant. What Hoffman, Kale, and Paquet showed is that whenever you have log n divided by n plus omega n, you already have.
Right, but I don't think you care about this one.
Okay, so let's discuss it. I think in the normalized Laplacian, that's exactly. But they're not correct. Then no.
Interesting is to understand.
Yeah.
The right-hand side.
For my argument, you can use probably very dumb ideas. I just wanted to give respect to this sequence of works that actually pushes this to log n divided.
Why would you expect H1 to be, large?
Do you know it's non-zero for?
Why do you know?
I really don't know whether it's zero or not. I have
Do you have any?
No, I think our work actually hints that maybe it is just flat zero throughout this range because we see that on both sides it seems to tend to zero.
So how should I interpret your main theorem then?
Maybe it's a null theorem. I don't know. That's my point. Like I really don't have any intuition to H. It would be lying to say that I believe that this is true. But I must say that there is a heuristic. If you think that a random object has so many covers that essentially all its covers are just identity, then this should be true.
Say again, if you believe that
a random object has so many covers,
so few
finite covers, that it essentially only has the identity covers. So it's not only non-residually finite, it is highly non-residually finite. Like it just doesn't have any finite covers, which are not just unions of the base simplicial complex. Then this is true. Okay.
It's
okay. So almost covers. If every almost cover is close to being the identity, like just union of copies of the base thing, then this should be true. So if you are so pessimistic about the covering theory of these random objects, which already tells you that they are non-sophic. So somehow, if you already believe that they are non-sophic, but they are so non-sophic that essentially all their almost covers are just very close to being stack of the base thing, very close to being stack of the base thing, then this is true.
Can you somehow kind of amplification, like start with something where there are some almost covers, but then move to something where fraction of evaluation is even worse.
Again, like you need to formulate it for me to actually like know how to answer, but I don't know. Maybe there are some amplification techniques here.
So under what assumption, like under the assumption that you said this H1 will be true, but what is H1?
What is little h1? But I don't know.
Yeah, like you said, like if all the cover are identity, then what is H1 that you could predict?
Essentially constant.
Okay.
Yeah.
Is it because like the degree will be the?
That's exactly. I'm saying if you have a good structure theorem of almost coverings of these cochains with small coboundary, and you can show that essentially to be a cochain with small coboundary, you're essentially some permutation of just the identity, then it will give you that this thing is bounded away from some constant close that comes essentially from the property tau constant. Okay, so like
Okay.
will be something equivalent to the things that we see there. But again, that's a very optimistic type of viewpoint. I don't know, like or maybe pessimistic. I don't know. Do you love covers or hate covers?
If you phrase it in terms of coboundary expansion, you have a complex, let's say it's n vertices, it has n to the 2.1 triangles, right?
Yeah.
Okay, random. And you want to show that it's a good, this complex, the coboundary expander, even without the parameter, not with a constant, yeah.
You ask me if I can say something?
Yeah, no, maybe it's a direct,
maybe.
it's a direct test of your,
Yeah.
yeah, that's what you asked. The assumption in your main theorem is that this is a reasonable coboundary expander.
Yeah.
Random set of triangles of about a little more than a square triangle.
And moreover, with an infinite sequence of courses.
So the word, I would just use the word cocycle expander, not coboundary expander.
I would say for any group, yeah.
Avi, it's actually important that I use the word cocycle expander, not coboundary expander, because that's exactly the question whether you even have finite covering spaces or not. Because if you have any covering space, you have cocycles that are not coboundaries, and then you would not be a coboundary expander in the usual sense. Like, what is coboundary expansion? It's being a cocycle expansion, so almost cocycles are closed cocycles, and all cocycles are coboundaries. So here, all cocycles being coboundaries is exactly saying that you have no non-trivial finite covering spaces. And that's exactly the optimistic version of that I said. Like, the coboundary expander will be in the parameter setup where I'm saying that you're in the optimistic sense.
I just want to think about it.
Still cocycle expander.
Yeah, that's my point. Cocycle expander. I just wanted to say that's the correct word to say. Yeah, let's finish, right? Let's go to it.
Okay, thank you very much.